Hello, today we're going to just really briefly introduce enthalpy of reaction. So when you have reaction, they could give you the heat information in one of two ways. They could tell you what the delta H is, that's enthalpy or heat of reaction. So in this one, this is the reaction, and our delta H is positive 180 kilojoules per mole of reaction. And we know it's positive, so it's endothermic. I highly recommend annotating as you go. The other thing they could do is actually list the heat as a reactant or product. So because it's endothermic, it's going to need to absorb that heat over the course of the reaction. So you can put it actually on the product or on the reactant side. So if you see heat on the reactant side, that's endothermic. If you see heat on the product side, that means it's exothermic. Or you would say the delta H is negative. Now, typically you're going to see it in kilojoules per mole of reaction. Sometimes you'll see joules per mole of reaction, but most of the time it's kilojoules per mole reaction. Now, what that means is, remember, 1 mole is 6.022 times 10 to the 23rd. So if I say per mole of reaction, that's the kilojoules it takes for the reaction to happen 6.022 times 10 to the 23rd times. All right. And the way that we would kind of look at that is when you do this reaction, when you do that reaction once, you have one N2 molecule reacting with one O2 molecule, and it produces 2 NO molecules. That's for every one time the reaction happens. So you can scale that up to moles. Every time the reaction happens 1 mole of times, right? The reaction happens 1 mole of times, you use 1 mole of N2 and 1 mole of O2, and you produce 2 moles of NO. So heat is typically given in per mole of reaction. So it just tells you how many times the reaction is happening. Now we can also use calculations from that. Now it says, so here's a couple examples. The first one, how much heat is required to react 2.4 moles of N2 with excess O2 to form NO. So I have 2.4 moles of N2. I would actually write this differently. So I'm just going to ignore kind of this one. I would write it, if I have 2.4 moles of N2, every time the reaction happens a mole, right? 1 mole of the reaction will take 1 mole of N2, just like that. Or you could even write it like this. Every one reaction has 1 N2 molecule. I like this way a little bit better because I think it's a little easier to understand conceptually. So I have 2.4 moles of N2. The N2 cancels, and so you'll have 1 reaction. And then from here you can get to the 180 kilojoules for every 1 mole of reaction. The moles cancel, the reaction cancels. And so that's how you get the 430 kilojoules. Let's do another one. I'm going to get rid of the mole number here so I have space. 25 kilojoules of heat was absorbed. How many moles of NO were produced? So, and again, I don't really like how this one's written. You can write it that way if you choose. I like to write it using the moles of reaction. So 25 kilojoules is how much is absorbed. All right. I have 180 kilojoules for every 1 mole of reaction. I want to go ahead and cancel out those kilojoules. We're looking for moles of NO. Every one time the reaction happens, 2 NOs are produced. So the reaction cancels out that way. So now I'm left with the 0.28 moles of the NO. So I really recommend you add in a step there where you're showing how you're relating the moles of the substance itself to the moles of their overall reaction. And please make sure you're paying attention to that as well. Okay, so they give us a reaction. We know it's exothermic because it's negative. If you were to react 7.25 moles of H2 with 9.34 moles of O2, how much heat would be released? So they give us two amounts of reactants. This, going back to Unit 4, you need to figure out which one of those things is the limiting reactant first. So I'm going to go ahead and test both of them. There's 2 H2S for every 2 moles of water produced. You can use either one, it doesn't matter. But that means you're going to produce 7.25 moles of water from the H2S. Now let's test the oxygen. Moles of O2. There are 3 moles of water used for every 2 moles of H2O produced. So that will give us 6.23 moles of water when you calculate that. Now this number is smaller, so that means the O2 is our limiting reactant. So the H2S is in excess. I don't want to use that for my calculation because you have extra of it. We don't know how much of it's used. So I'm going to use that 9.34 moles of O2 to calculate for the heat of the process there. You always want to use the limiting reactant. So we know that there are 3 oxygen molecules for every 1 time the reaction happens. I want to make sure I get that into moles of reaction, so I can use my heat. Now, it's saying how much heat would be released. We know it's exothermic. I'm just going to go ahead and use the magnitude of that heat energy. Oops, I'm going to put it on the top. The 1120 kilojoules per mole of reaction. That way the moles cancel and the reaction cancels. And so when you go ahead and divide and multiply, you get 3490 kilojoules released. You could also say that the heat for the process is, so Q equals negative 3,490 kilojoules. But since it was phrased how much heat is released, we can just list it as a magnitude. 3,490 kilojoules was released. Okay, let's look at one more example. This time we have hydrogen and oxygen reacted from water, and we know it's exothermic because it's negative. If you perform this reaction and produced 92.1 kilojoules of energy, how many moles of water were also produced? So I want to go ahead and start with that 92.1 kilojoules. Okay, it produced that amount of energy, right? It released it. I'm going to go ahead and use the heat of a reaction, but I'm going to use it as a magnitude because that's how much was released. Right? For every 1 mole of reaction, kilojoules cancel. You could also do it the other way and say that they're both negative, but it doesn't matter. Now we want to know how many moles of water. So every 1 time the reaction happens, 2 water molecules are produced. So I can do the 92.1 divided by the 41.6 times 2, and you get 0.382 moles of water. A good little check here to make sure that you're paying attention to your signs. You can't have a negative amount of moles. So if you wound up with a negative amount of moles, then you knew you did something wrong with your signs. So I think it's useful to maybe just use the magnitudes when you're doing these calculations, and then if it's phrased in a way that you need to use the sign, you can pay attention to that at the end and give the sign at the end.